Hi, everybody. Welcome. My name is Bitan. Today we're talking about our paper UniPar, a unified LLM-based framework for parallel code translation in HPC. And this work is done under the supervision of Oren. So let's get started. So this paper starts where a lot of the work in our lab starts, and it's best shown in this paper from a few years ago, where we looked at all the parallel APIs we could find on GitHub. And you can see them here in the HP corpus. And we see that there's a huge variety of different parallel APIs and a huge data imbalance between APIs like OpenMP that are pragma-based or like directive-based parallelization and APIs that are language-based, like CUDA, for example. And there's also some that are vendor-locked, like CUDA and HIP, that's somewhere here in the other. And all these different APIs are slowly growing in popularity as time goes on. And so our mission is to try and make this process of writing parallel efficient code as easy as possible and making it platform agnostic as simple as possible. And so the first works in this kind of area of translation or parallel code translation started with static translators that are like compiler based. Um, and the main problem with this approach is that it's very difficult. So it takes a lot of work. And so works like Q2CL that are academics, came out of academics, have a hard time keeping up with the new versions of APIs that are continuously being released. And because it's a lot of work, also the tools that came out of the industry like Cyclomatic and Hippify are very narrow scoped. So they only focus on a specific set of languages that is the language that matter to them. And so it's difficult to add more languages to any given solution, and it separates this task of parallelization and translation between parallels. And so the next iteration was neural translation. So taking a bunch of data from this translation task, giving it to a neural network, and it spits out a new translated code. And so this helps a lot with the work to keeping up with new versions, but it takes a lot of data. So we see a huge focus on OpenMP, which is the one we saw with has the most openly available data. And also, since it's directive-based, works like OMPAL can focus on each parallelization loop individually. And so the early neural networks that don't have enough context can focus on specific uh, loops and parallelize them individually. And even when you look at a code Rosetta, for example, that works on CUDA, it's still only one language and only the one with the most data available. And also, most of these works focus on parallelization and not translation between parallel APIs. Um, so in recent months, we've seen a huge decrease in the prices of online APIs for large language models, and also in the availability of open language models that are free to open source and free to use, that are all demonstrated to have good performance with code, and some even with parallel codes. And so the reason that all these LLMs became popular in recent times is because of their promise for generalizability. So they promise to have the ability to zero shot, so trying a new task without any experience in it relatively well. Um, and when we pair that with the larger context, so it overcomes the variety of kernels that we can work with, and new available APIs to fine tune on the cloud, we get a much potential for a much more generalizable solution. And so what we came to ask is, can these LLMs be this a backbone for this magical perfect translation pipeline that we're looking for that can do both serial to parallel and between different parallel APIs. That it's like easy to implement because we don't need to handcraft rules, and it's easy to maintain um, because we have the data approach, and it's easy to upgrade because of the generalizability of our backbone, and we can add future languages a lot easier. And so what we did in our research is we started with GPT-4o Mini and Llama 3.3 70 billion as the base model. And we tried to look at different approaches to improve their performance and see if we can build this translation pipeline using these LLMs. And so the different approaches we looked at was temperature changes, few shot examples, so adding examples of how to translate into the prompt, And then we bring out the big guns with fine-tuning the model and a very simple agent pipeline to make the model interactive. And you can read a lot more about all these approaches in our paper. Let's focus for a second about the agent pipeline. So what we tried to do is we tried to take the absolute simplest to implement approach for making the process more dynamic, similar to how real programmers interact with their code. So they do some task translation, they try to compile it, they see what the feedback is, and then they learn from it and try to change it. So the absolute simplest pipeline we could think of um, was like we take, say, an accuracy kernel here in CUDA, we give it to an agent, which could be any LLM with any of the previous approaches added onto it. It gives us some translation. We compile this, and then we give it to a separate LLM that takes the compiler error along with the original code and tries again to fix the translation. So we just tries this 3 times, try to run a test 3 times, and that's it. And you'd be surprised even this simple translation has a lot of benefit to our end result. Okay, so in our evaluation, we worked with Hackbench. We took where we have many different implementations of the same kernels in different APIs, and we took all these kernels and we turned them into a data set we call paratrans, where we took tuples of translation pairs. So we have serial to OpenMP, serial to CUDA, CUDA to OpenMP, and OpenMP to CUDA. And what we're basically looking at is the compilation rate. So the average number of kernels that compile successfully after we translated them. And also the validation rate, which is the number of kernels that pass the internal validation test that's available in Hackbench. And so we're looking to see what are the out-of-the-box validation compilation rates and how we can improve them. Okay, so when we're looking at the temperatures, we can see that lower temperature gives us a consistent, the most consistent result, which is something we're familiar with other literature, but it also gives us the best results. So we see that it's consistently some of the best results in the lower temperatures, particularly when we go to the max output tokens that are higher. So the larger variety of kernels will be available when we have a larger max output tokens. And we see that across the different models we tried, they all have consistently better performance when we go with the lower temperatures. So that's something to keep in mind when we're training these things. Next, we look at the few shots. And here we see, actually, interestingly, there is no significant impact to adding the few shots. So across the different translation tuples, we can see here on the right, and across the different categories that Hackbench has for the different kernels, we see there's no consistent improvement when we add examples into the prompt. And actually, when we added a specific example and gave it the exact same translation tuple to try and translate, we saw that sometimes it even missed in these scenarios. So it missed some small detail that caused it to not compile, even when it had the exact same kernel that it was supposed to spit out as part of the prompt. And so we know that fine-tuning that few shot is not very helpful. And so we bring out the next one, which is fine-tuning. So we split out our data set into training and testing. And we can see that fine-tuning the Llama model gives us a nice little improvement in the compilation rate, but a very big improvement in the validation rate. So the number of kernels that actually do what we expected them to do, and not just correct code that functions, has grown a lot, almost 3x on average between the different translation tuples. So fine-tuning definitely helps a lot with this translation task. And finally, we look at the results from the agent pipeline that we talked about earlier, and we can see huge improvements, both for the base models and for the fine-tuning model in compilation and validation rate. And the best part is that we see that the best result is over here in the validation rate for the fine-tuning model. So we have stacking benefits from fine-tuning and the agent model. Yeah, so to summarize what we looked at, we tried to look at base LLMs and how they perform for this translation task. And we see that by themselves, without any additions, they're not very good. So they get just under 50% compilation rate and just under 20% in the validation rate. But once you lower the temperature to make it more consistent, and you add in fine tuning and even just a simple agent pipeline, the results jump up to 75% compilation rate and above 40% or around 40% in the validation rate. So this gives us a lot of hope that maybe this could be this perfect solution that we're looking for to base our eventual translation pipeline on. And so in future work, aside from additional evaluation studies that we're looking into for the things we did in this paper, we're looking into a lot more improving the agent pipeline to be more sophisticated and more tailored towards specific tasks for HPC, and also how we can improve the model's behavior to work well with the agent, or just to be better given the feedbacks from the agent. And finally, we're looking at the different architectural changes that we can add that are still bolted on to external models, but help improve performance in the model level itself. So thank you guys for listening, and Tal will be here for questions.